Yeah, we derived an expression for the probability of error, and this, the previous expression, that PE equals summation small m goes from 1 to capital M, PM summation So this is known as symbol but since each symbol can contain k bits, not all bits in error. Example, consider this 0 0, or rather 0 1 1 0, or should it be 1 1 1 0. Suppose this is the constellation. Then this is gray coded. So if this gets misdetected as this, then the higher bit is okay, the lower bit is misdetected. Here the lower bit is okay, the higher bit is misdetected, and so on. So in nearest neighbors, you get just a one symbol error or one bit error for each symbol error, right?
Sir,
Yeah.
sir, is PM is basically probability of SM?
Yes.
Okay.
So in general, and we define PB as the probability of bit error. Then we have the following inequality relating probability of bit error and probability of symbol error. PB less than this. This inequality holds. Makes logical sense.
So what is K?
K is the number of bits per symbol.
So K into PB represents all the bits being wrong, like complement of the bits, like we are getting.
Yes. So this is that. So in a symbol, what might happen is that a symbol may be in error if one bit is wrong, two bits are wrong, up to all the right. Any of these cases you will have a symbol error.
Yes, sir.
So,
But sir,
yeah,
sir, you have written PB is less than equals to P less than equals to K into PB. Like P is the error probability, symbol error probability, but PB is the
bit
bit
error
error
probability.
probability.
Yes,
Okay.
I said this PB as the probability of bit error.
Then why
So,
exactly? Okay, okay, got it, got it.
so first consider this one. So if symbol error,
Sir, just one small query. If
yeah,
if K is large enough, that then that can be greater than 1. I mean, that which doesn't make sense.
it'll make sense. Wait a second.
Okay.
Large enough. So I'll answer that as well. So symbol error probability is PE. Then if every time a symbol is in error, all its bits are. This is one case. Sorry, this should be uppercase K. Fine. So these are the two extremes, and the probability of bit error lies between these two extremes. And answering Rahul's question, so consider, or in general, we consider constellations with 256 or 1024 Quam is, from what I know, the largest constellation that is used practically.
And sir, instead of K times P, shouldn't it be like probability of error should be 1 minus PB to the power K, right? Like
So that Rahul
everything is
is,
right minus
yeah,
1.
that is. So I'll let me finish this one point, then I'll come to the second point.
Okay, sir.
So this is, so K or K is of the order of 10, right? At most. Whereas practically we like to operate PE so fine, Rahul.
Yes, sir.
KP isn't large enough.
Yeah.
Great. So one problem is sorted out. The second problem is, so can you repeat the question?
So yeah, that like whenever we consider the send signal as an error is even if one bit is wrong, then it is error, right? So we have to consider for all
Yes.
type of combinations. So
So
the
like
probability of error should be like
One
if
at
we
a time.
consider yeah, if we consider probability of one bit error as PB, then probability of
So,
error should be one
one thing,
minus
Rahul, one thing. So
yeah
probability of symbol error
yeah.
or PE, or based on whatever we know,
Hmm.
on whatever we know, we can directly calculate PE, but we do not have a direct mechanism for calculating PB. Therefore, we express the bounds on PB as the function of P.
Yes,
Fine,
sir.
it's not the
I
other way
agree to
around.
this. Okay.
It's not the other way around. Since we cannot obtain PB directly, there is no point in chasing PE through this.
Okay, but we can establish the bounds using what I said, right? Like one, the most error would be all the bits are wrong, and
Yes.
the least error would be like one of the bit is wrong. So we can
Yes.
write its probability, and then like instead of
Yes.
writing it k times, shouldn't we do that?
So one point is that that depends heavily on the kind of encoding you use. So
No,
you can see
probability is
that
independent of that, right?
Rahul.
I mean, okay,
Yeah.
okay, sir. Sorry,
So
I'm sorry.
yeah. So suppose in this constellation itself, the one that I drew here, instead of gray coding, if you use straight binary encoding, what happens?
The symbol's position changes.
The symbol's
So
position changes. So uh, so now we know that a near from whatever we have discussed till now, we know that the nearest neighbor probabilities are more likely.
yes,
So this is unlikely to jump here, this is unlikely to jump here, and so on.
yeah,
So now if I write this as 1 0 and this as 1 1, so a nearest neighbor error, now instead of having a 1-bit error, this will be a 2-bit error, and this to this. So these nearest neighbor errors will be 2-bit errors now. Similarly, these one. So vertical errors will be 2 bits now.
yes.
So the just on the basis of how you write the constellation, the entire bit error probability changes, but the symbol error probability doesn't change.
Okay. But just one more clarification.
Yeah.
But while we are calculating the error, we consider all possible kinds of not just nearest neighbors, right?
Yes. Yes. We will reduce it to the nearest neighbors eventually.
Okay.
So we'll see that these integrals become quite ugly quite fast.
Okay.
So we have to reduce everything to something that is tractable.
Okay.
Okay. So we do a lot of simplification after this. Yeah, Shubhashish.
so like isn't one bit error is more probable than all the bits being an error, because there
You
are
can
k
never say
number of
that.
possibilities then in the first case. But
You can never say that. They are so yes, I agree that having 1-bit error is more likely, or rather it depends on the channel. So what if the error, the number of occurrence of error follows a Poisson process
hmm.
with some k. You don't know what process. So modeling the occurrence of an error is a separate issue.
So
One
then,
error. So one error out of, say you have a 10-bit stream, suppose.
okay, sir.
Okay. We discussed this in the last semester Viva question as well. So a lot of you might know it. So if I have a 10-bit stream, what is the worst case? Or when can I say that I'm in actual trouble for this 10-bit stream? When I receive 10 bits, what will be the worst case?
It's the probability of
Always.
error half, like
Yeah.
Yeah, when you tell me that half of these are in error.
Yeah.
So now I receive 10 bits and I 10 arbitrary bits, and you say that out of these there is a 20% chance of error. So you know that 2 bits out of those 10 are in error, but those can be 2 subsequent bits as well. So one entire symbol can be in error. Those can be 2 bits on the edges. Those can be 2 bits anywhere. So you
Yes.
cannot simply kill off the possibility that yeah, it can be a burst error. That is, there can be a sequence of bits that is in error. You cannot rule out that possibility. The error is independent. Any 2 bits can be in error. A sequence of error is less likely. A continued run of errors is less likely, but it is still possible.
Okay.
An octopus predicting the outcome of World Cup is unlikely, but has it not predicting the outcome of 8 World Cup matches, so one after another, is unlikely, but has that happened?
yep.
Yeah, precisely.
Okay. Got it.
So basically what that was is that there are so one of the outcomes is not exactly random. It depends on the skill of a team, but so a random number generated somehow matches up to the skill of a team is unlikely, but yes, that has happened. So anyway, now was it 8 or was it 7? I remember 8. Now let us assume that seat right, and let or rather, since we have used F, if we can write it like this, then a part of that vector is only dependent on the other values, R1, and we have R1 with us.
So could you repeat it once again?
So if I can write the received vector R as this, and I can write the PDF of R1, joint PDF of R1, R2 like this, without
Sir,
R2 depending on SM.
So the second one
sir,
should be
Sorry?
the second one, it should be R2 given R1 comma SM, right?
Yeah, that's what I'm saying. If I can write it like R2 depends only on R1 and not on SM, if it can be done.
But you are assuming that it is not dependent. Like that's
Yeah.
why you're not including SM in
Yes,
the right.
if can be written as.
sir, R1 and R2 are symbols received at two different or
No,
vectors received
R1
at two
and R2
different.
are the partitions of the same received symbol.
Oh, okay.
So I'll repeat. We are partitioning the received symbol vector R into R1 and R2, where the new vector R1 depends on the symbol, but R2 does not depend this way. But R2, sorry, R2 does not depend on S, it depends only on R1. It sorry, yeah.
So doesn't this mean that we are only like using that R1, whatever the, sorry, we are
Yes,
only using
yes,
R1, like we
yes.
are reducing the
Then
number of possible symbols.
yes, yes, precisely. So in such a case, we can extract R1 from R and work only with that, and R1 is called the sufficient statistic for fine. Fine.
Yes, sir.
So sufficient statistics, detection estimation, people, this is close to what you have done there.
Yeah.
Yeah. So now,
Sir, but when we were encoding SM when we were transmitting SM, and then some noise got added, and what we received was R. So shouldn't the entire R be dependent on SM and not just? I
maybe
mean,
you
how do
have,
we?
maybe your receiver is something, or maybe your receiver is inefficient.
Okay, sir.
So
Sir, but
this is,
R1 is sufficient information to get back SM.
yes, if it meets this condition, if this condition
Okay,
is
sir.
met. So now coming back to m hat equals this is where we started. And we had reduced it to what did we use? Eta m or lambda m? Eta m, I believe. Let me look at the previous lecture. Xi m, because eta is noise. Right? This is where we slightly switched our discussion. Agreed?
So what
Equivalently,
was Xi?
Yes, sir.
Xi
Like
m was
was not there
the
last.
some function, the log times noise times the prior probability. You can look at the derivation in the previous class.
Okay, sir.
So this and but right?
Sir,
Yep.
in last lecture you had removed Xi because it wasn't dependent on M, but why exactly here?
I had talked about the special case where Xi m, where the prior probabilities are all equal.
Okay.
There it says that for Pm equal to 1 over m or Xi m being independent of m. That was a special case.
Okay. So here we are taking a general case.
Yes, here we have come back to the general case.
Okay.
Okay. I'll go back. We will go back to that special case again. So now this R, the mod of R is independent of the index m, right? Or norm of R is independent of index m, right? So m hat equals arg min sm square minus 2 right?
Yes, sir.
So again,
Sir, R is dependent on SM, right?
R is the received signal. R is we are doing everything conditioned on R.
So, okay.
Special case IM being, and we don't know the dependence of R on SM, or we don't know what is SM. That's what we are trying to find out. The symbols being from symbols all having equal energy. M hat equals fine.
Yes, sir.
So this is what? This is maximizing the correlation.
Yeah. Yes.
Minimum distance, minimum Euclidean distance, maximum correlation. You have heard of these tricks in machine learning.
Yeah. Yes, sir.
So just a second.
Sir, so is this another way to write the same thing that we derived in the last lecture?
This is for equal energy signals. Yes. If SM comes from a circular constellation, then this is, yeah. Yeah, so this is a special, okay, just a second. Fine.
Sir. Sir, this could have been done yesterday only, or when we were doing that part. So why exactly we went through such a rigorous procedure, and then now we did the same thing?
So short answer, this is how the book did it. I agree with you.
Okay.
Okay. But since I'm following the book and we actually that one or the probability of error. So I don't know why that guy started defining the probability of error and then did this, but these are two separate topics. Or rather what they did was they took a break with probability of error and then started discussing this again.
Yes, it felt so.
Yes.
Like, this isn't related to what was taught just a few minutes back.
Yeah, so I agree that probability of error was possibly like a side note, but that will come back. Anyway, so again, right? This is right.
Yes, sir.
So these are so DM is the region for the mth symbol. Now we look at the boundary. So the decision boundary. So this is a hyperspace, n-dimensional hyperspace. So the decision boundary will be a hyperplane. So let's look at the structure of that hyperplane. Sm plus xi m equals not square. Right? Fine.
Yes, sir.
So I do some. The first thing to do here would be to complete the squares, or rather what I will do is,
Sir,
yeah,
just now you stated that it should be less than the right side. Now you have equated both of them.
I said that this is the boundary, or I will write this thing. Why not? Yeah. So the equation of the boundary between the mth and the minus im. Fine.
Yes, sir.
So no square here, no squares. So you complete the squares and do some trickery, and then you can show that this reduces to R Hermitian S minus Sm minus Sm dash equal some, say, some G, where G is a function of xi m.
So it doesn't matter if it is a plus or minus EM. It doesn't, right?
Xi plus or minus xi m, it won't matter much. What matters is that it reduces all these boundaries reduce to planes, which is, I believe, obvious from the structure of the equation, that these will have planes as boundaries.
Yes.
So that is the only thing, that the for n dimension in the n-dimensional space, the boundary between two decision regions will be an n-dimensional hyperplane. Fine.
Yes, sir.
Yeah. Yeah. Also, yeah. So this we have talked about. Now consider case with binary antipodal signaling such that S1T equals ST S2T equals minus ST. Or rather, S1T equals root over ES, S2 simply this. S1 root over ES, S2 equals minus root over ES. Fine. Then with fine. Then D1 equals R such that R minus E root over ES the whole square plus 2P is greater than plus root over ES not whole square here. Was there a square? And there was a square, right? So plus fine. This is fine.
Yes, sir.
So this equals R such that R square plus ES sorry, this R square plus ES also comes here plus R yes. So yeah, this was a minus. This was a minus. Minus. This is also a minus. And not natural log of fine.
So n naught is
N naught is sorry, N naught by 2. Not by 2. Yeah. So N naught is the noise. N naught by 2 is the noise variance. We showed that 2 or 3 lectures back. Fine. So cancels, cancels. Or plus N naught natural log of P is greater than or is less than or
Sir,
yeah.
I think that should be 4R root ES. Like, I think at the top in the
Yeah, yeah,
second.
yeah, 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 yeah. Yes. So this should be 2 here and this should be 2 here. And for P equals 1 minus P, that is for equiprobable symbols, you simply get R 1 this. So you whenever you transmit 1 or whenever this is greater than 1, you whenever this is greater than 0, you declare it to be 1 was transmitted. Whenever this is less than 0, you declare that a 0 was transmitted. Fine.
Yes.
Great. So this makes some logical sense. Now coming back,
Sir?
yeah.
So you meant that like there will like when both P is equal to 1 minus P, there will be a threshold like above which it like a midway threshold above which it will be considered as 1 and below which it will be considered as 0. Like that
So
you
when
were
P
saying.
equals 1 minus P, the log thing becomes, when P equals 1 minus P, both of these equal half and this natural log of this thing is 0.
Yeah.
So the threshold becomes 0.
Okay, so less than 0 it is 0, greater than 0 it is
Yes.
1.
Yeah. So yeah. So I think it will be good to stop here, because I don't want to start off. So there is probability of error analysis now. So should I write that, or should we stop here? I think it's
Sir, we can.
Stop here.
yeah. I think it's a good idea to stop here and then continue tomorrow. So tomorrow again there is okay. So a lot of people told me. I'll just stop recording. Yeah. So